Hello everyone and welcome to day 2 of integrals. We're going to look at more of the definite integral we ended off with. This just is a recap of what we talked about last class with the limit definition of the sum. So if we look at the first question problem, we have the definite integral with the bounds 2 to 5 of the function 3 with respect to x. So it's really y equals 3 plus 0x, because there's no x there. So 3, we just know looks like a straight line. And we want to know what the area bounded by the x-axis is of that rectangle from 2 to 5. Well, we know the height is 3, the width is 3, and so therefore we know that is 9. What happens if I give you this problem? Y-intercept of -1. We know a slope of 1, so we know that's 1. This is -1. We're bounded from 0 to 3 of this function. Now, 0, notice the problem here. We have this area that's underneath the x-axis versus this area that is above the x-axis. And we have an area bounded that is underneath the x-axis and an area that is bounded above the x-axis. We can state that since we have two different triangles here, we can find the area of a triangle. It's going to be the green triangle plus the blue triangle. Well, if we look at the blue triangle, the base is 3, the height is 2. And so we're going to get 3 times 2 divided by 2. We know that the area is 3. In this case, notice it is below the x-axis. Really the height, the base is 1 here, the base is 1 right there, but the height is -1, and so we really have a -1/2. And so therefore that the integral equals 3 plus a -1/2, which is 5/2. The key being that when you are below the x-axis, the height is really -1, and therefore it's negative area. When it's above the x-axis, the height is positive, and so you have positive area. The last thing I wanted to look at with this is we can also state that the area here, the integral, can be split up into two different integrals, as I showed with the blue and the green. We could do the integral from 0 to 1 of x minus 1 dx, plus the area from 1 to 3 of x minus 1 dx. All this is showing you is that the area from 0 to 1 is -1/2, plus the area from 1 to 3 is 3, and that's how we get 5/2. It's another way you could have drawn it, or written it mathematically. Couple properties here. The integral from a to b of f of x equals the negative integral from b to a. If you were looking from a to b and we go backwards, it's just the negative portion of it. The area from a to a, well, if I have from a to a and I don't move at all, what is the area? Well, the width is 0, and so the area is 0. We have some properties that should look very familiar to the derivative properties that we've looked at. Look at the next page. So we have this picture here, and you'll notice it's color-coded. We have a green. This is positive area. This yellow, which is negative area, and this purple or pink, which is a positive area. So the area from A to B is 2. The area from B to C is -4 again. Why? Because we are below the x-axis. Area from C to D is 1. And so what is the area from A to D? Well, we know that's the integral of A to B plus B to C. And this is incorrect notation. Just know that I understand that. And C to D. Well, that's just 2 minus 4 plus 1. And so we're going to get -1 to be the area from A to D. It's just all those areas added up. One other property, and we can look at this by drawing it out, but if we have the property of A to C, and we have the property from C to B going backwards, we then, so A to C minus C to B, we're left with the area of A to B, which should make sense. Again, this we can talk about going backwards if we label them A, B, C, and therefore, if we go backwards, we're subtracting that area and we're left with just A to B. So using that theorem, if I have 2 to 9 and 5, if I know 5 to 9 is 8, and 5 to 2, which is 3. Now, careful here. If 5 to 2 is 3, we really want to rewrite this as 2 to 5, which is negative 3. Again, using the property that if I flip the bounds, I can negate it. So we have negative 3. So what is the area from 2 to 9? Negative 3 plus 8, which is 5. Now, we're going to get into the fundamental theorem of calculus, and I'll talk about more of this later. You can read it. Isaac Barrow, Newton, and Leibniz all developed calculus. The fundamental theorem of calculus states that if you're given the integral with bounds a to b, lower bound a, upper bound b, of a function, then what you can do is take the integral of the function, so this is going to be the integral, the capital F is the integral, and evaluate that integral, that function, at b and at a, and when you subtract them, that will give you what the definite integral is. In the example in the very beginning when we did 2 to 5 of 3 dx, when we look at that and we take the integral of that, the integral of 3 is 3x, and we're going to evaluate it from 2 to 5, we're going to, this is our capital F of x, and what I'm going to do is take our upper bound, find f of 5 minus f of 2. That's exactly what this is saying right here. So f of 5 is 15, f of 2 is 6, and you get 9. And that was what we just learned at the top of page 1. We got the integral to be 9, the area under the curve to be 9. And so this is the fundamental theorem of calculus part 1. We're going to do part 2 in class the next day. But this is what we're going to use to solve definite integrals. So we have 9 examples here. I'm going to do 4 of them. You can do 5 of them, and I will put the answers up on the video when you guys complete them. So I'm going to do these 2 and then the 2 middle ones in the second and third row. So the first example, the integral from 0 to 3, lower bound, upper bound, of the function x minus 1. Put an equal sign. I know what the integral of x minus 1 is. We're going to do x squared over 2 minus x. And we're going to evaluate it from 0 to 3. So this is our big f of x. I'm going to plug in 3. 3 squared over 2 minus 3. Subtract it from 0. Well, 0 divided by 2 is 0, minus 0 is 0. So we're left with 9 halves minus 3, which is going to give us 3 halves. And we're done. That's it. So you're going to take the integral, evaluate it at the upper bound, and subtract it from the lower bound. Let's try this one. We know we can rewrite this as x to the 1/2. And so we're going to get x to the 3 halves divided by 3 halves, 1 to 9, which is really 2/3 x square root of x cubed. Excuse me, 1 to 9. And so we're going to get 2/3 of 9 cubed minus, so we're going to get, square root of 9 is 3, 3 cubed is 27 minus 1, and it's going to be 26. 26 times 2 is 52 divided by 3. A trig one, don't get too confused. We know the integral of cosine x is positive sine x. We're going to evaluate it from 0 to pi over 2. Again, if you need to remember your unit circle, sine of pi over 2 minus sine of 0. Sine of pi over 2, we're looking at the y value, so 1 minus 0, which equals 1. And for the last one, the integral of 1 over x is ln of the absolute value of x. from negative e to negative 1. So we know it's the ln of the absolute value of negative 1 minus ln of the absolute value of negative e. Well, we know the ln of 1 equals 0, and we know that the ln of e equals 1, so you're going to get 0 minus 1, which equals negative 1. So, if you want, go back and try some of these. I'm going to pause it, I'll do the rest of them out, and then you can check your answers. So I hope that you did these problems and did not just copy or are going to copy these answers, but in red are the answers. 5 halves, x squared times square root of x is 5 halves. So I got that. With this one, hopefully you notice that 3 cubed divided by 3, a good hint of doing mental math anytime. 3 cubed divided by 3, the 3's cancel, so you're going to be left with 3 squared, which equals 9. So that's how I got that. 1 over cosine secant, so you're going to get tan theta. Right, the integral of secant squared is tan theta. And the last one, while it comes up, you could bring out the 5, ln of e to the ln. We're left with what the ln is. E to the 0 is 1. And with this one, calculator works the best. Please read and enjoy the joke of the day. See you in class.